Welcome to the ultimate guide for conquering Apache Kafka interviews as an experienced Java developer in 2026. In today's competitive landscape, interviewers are looking for more than textbook answers. They want to know how you've handled Kafka in real-world production scenarios. This video will walk you through 40 essential Kafka interview questions, each with practical, production-aware answers. Whether you've worked with Kafka in Spring Boot microservices, managed consumer groups, or tackled dead-letter queues, this guide will help you stand out. Let's dive in and build the vocabulary and confidence you need to ace your next Kafka interview. Interviewers today want to hear about your hands-on experience with Kafka in production, not just theoretical knowledge. They're interested in how you've solved real problems, like handling message backlogs, debugging consumer lag, or ensuring data durability. Sharing stories about how you've optimized Kafka clusters, managed failures, or improved throughput will make your answers memorable. Remember, the days of simply reciting Kafka is a distributed messaging system are over. Instead, focus on practical scenarios and lessons learned from your own projects. Let's start with the basics. What is Apache Kafka? Kafka is a distributed, fault-tolerant, high-throughput event streaming platform originally built at LinkedIn. It's designed to handle real-time data pipelines and streaming workloads at massive scale. Think of Kafka as a commit log that never forgets. Producers append events, consumers read them at their own pace, and Kafka retains everything for a configurable duration. This architecture decouples your services, making them more resilient and scalable. Why is Kafka so popular in microservices architectures? In a microservices world, services need to communicate without being tightly coupled. Kafka enables asynchronous communication, so producers don't wait for consumers. It supports event-driven architecture, resilience, scalability, and provides a reliable audit trail. Unlike REST calls, which require both services to be up at the same time, Kafka allows services to operate independently, improving overall system robustness. Kafka, a topic is a named feed or category to which records are published. Think of it like a table in a database, but append-only. Partitions are how topics are split for parallelism. Each partition is an ordered, immutable sequence of records. Messages with the same key always go to the same partition, ensuring ordering per key. Partitions are distributed across brokers for load balancing, allowing Kafka to scale horizontally and handle massive workloads efficiently. Offsets are unique, sequential integers assigned to each message within a partition. They help Kafka track the position of messages. Offsets are managed per partition, not globally. Consumers commit their offsets to keep track of what they've processed, and you can replay messages by resetting offsets to an earlier position. This is a key difference from traditional queues. Messages aren't deleted upon consumption. The consumer's position is just a pointer. Consumer group is a set of consumers that jointly consume a topic. Kafka distributes partitions among group members, ensuring each partition is assigned to exactly one consumer within a group. Multiple groups can independently consume the same topic, enabling fan-out patterns. If you have more consumers than partitions, some consumers will sit idle. This mechanism is the core scalability primitive in Kafka, allowing you to scale consumption as needed. Kafka guarantees ordering within a partition, not across partitions. By using a message key, you can route related messages to the same partition, ensuring they arrive in order. If you need strict ordering for all messages, you can use a single partition, but this sacrifices throughput. In practice, most business ordering is scoped to an entity, like all events for a specific order, and using the entity ID as the key solves this cleanly. Replication factor determines how many copies of each partition exist across brokers. A typical production setup uses a replication factor of 3, meaning one leader replica handles all reads and writes, while two follower replicas passively replicate from the leader. This setup ensures fault tolerance. If a broker fails, Kafka can elect a new leader from the in-sync replicas, maintaining data availability and durability. In Kafka, the leader replica handles all producer writes and consumer reads for a partition. Follower replicas exist purely for fault tolerance. They replicate data from the leader but do not serve reads or writes. If the leader fails, one of the followers is elected as the new leader. This separation ensures high availability and data safety, as all traffic goes through the leader while followers stand by for failover. ISR, or in-sync replicas, are the set of replicas that are fully caught up with the leader. If a replica falls behind, it drops out of the ISR. This matters because Kafka's highest durability guarantee, AX equals all, waits for all ISR replicas to acknowledge a write. If the ISR shrinks to just the leader, you're effectively unprotected. Monitoring ISR shrinkage is crucial in production environments to catch early signs of broker stress. When a Kafka broker goes down, the controller broker detects the failure and triggers a leader election for affected partitions. Producers and consumers automatically reconnect to the new leader, and the failed broker's partitions are reassigned. If the number of in-sync replicas drops below the minimum required, producers with AX equals all will receive an exception to prevent data loss. This self-healing design is key to Kafka's reliability. Producer acknowledgements, or AX, control how many broker acknowledgements the producer requires before considering a write successful. This setting balances durability and latency. You can choose between AX equals 0, fire and forget, AX equals 1 leader only, and AX equals all in-sync replicas. In production, AX equals all combined with a minimum in-sync replica count is the gold standard for durability, especially for critical data. Let's break down the differences. AX equals 0 means the producer doesn't wait for any acknowledgement, risking data loss but offering the lowest latency. AX equals 1 waits for the leader only, which is a balance between durability and speed. AX equals all or -1 waits for all in-sync replicas, providing the highest durability but with increased latency. Choose the right setting based on your use case. Financial transactions demand AX equals all, while logs might tolerate AX equals 0. An idempotent producer ensures that even if a message is sent multiple times due to retries, Kafka stores exactly 1 copy. This is enabled by setting the appropriate producer configuration. Kafka assigns each producer a unique ID and sequence number per partition, discarding duplicates at the broker level. This feature is a prerequisite for exactly one semantics and is essential for preventing duplicate data in critical systems. Kafka provides 3 layers of defense against duplicate messages: the idempotent producer, the transactional API for atomic writes, and idempotent consumer logic. Even with these, always design your consumers to be idempotent. Processing the same message twice should produce the same result. This approach ensures your system remains robust even in the face of retries or network issues. Rebalancing is the process of redistributing partitions among consumers in a group. It's triggered when a consumer joins or leaves, crashes, or when partitions are added. During rebalancing, all consumption stops, which can cause lag spikes. To mitigate this, use static group membership to avoid unnecessary rebalances during temporary consumer restarts. Understanding rebalancing is crucial for maintaining stable, high-throughput system. When a new consumer joins a group, it sends a join request to the group coordinator broker, which triggers a rebalance. One consumer is elected as the group leader, who then assigns partitions to all members using an assignment strategy. Sticky assigner is preferred in production because it minimizes partition movement during rebalances, reducing lag spikes and improving overall system performance. The auto-offset reset setting determines where a consumer starts reading when there's no committed offset. Options include earliest, start from the beginning, latest, start from new messages only, and none, throw an exception if no offset is found. Choose earliest for event sourcing or replay scenarios and latest for real-time feeds where historical data isn't needed. When configuring auto-offset reset, earliest means the consumer starts at the very beginning of the topic, reading all historical messages. Latest means the consumer starts with new messages only, skipping history. Use earliest when you need to replay all events, and latest when you only care about real-time data. Understanding this setting helps you control how consumers behave in different scenarios. A dead letter queue is a separate Kafka topic where messages that repeatedly fail processing are routed. DLQs provide visibility into failed messages, prevent bad data from blocking healthy processing, and allow for reprocessing after issues are fixed. In Spring Kafka, the dead letter publishing recoverer handles this automatically, making it easier to manage failures and maintain system reliability. Kafka supports multiple retry strategies for failed messages. Immediate retry is used for transient errors, while exponential backoff is ideal for downstream service issues. Retry topic patterns route messages through intermediate topics with delays, and after all retries are exhausted, messages are sent to the DLQ. Always set a maximum retry count to avoid infinite loops and ensure failed messages are handled gracefully. Boost Kafka consumer performance, tune fetch size and concurrency settings, increase partition count for more parallelism, and use asynchronous or reactive processing. Manual batch commits can reduce broker round trips, and scaling consumers up to the partition count allows for linear throughput scaling. Always monitor and optimize your processing logic to avoid bottlenecks. Consumer lag is the difference between the latest offset and the consumer committed offset. It indicates how far behind a consumer is. High lag means your consumer can't keep up with the producer rate, which is a critical production alert. Always monitor consumer lag to ensure your system is processing messages in a timely manner. Debug Kafka lag. Start by measuring lag with tools like Kafka consumer groups, SH, or monitoring dashboards. Identify slow partitions. Check consumer logs for long garbage collection pauses or slow database calls, and review Maxpol record settings. Scaling consumers and profiling processing logic can help resolve bottlenecks and restore optimal throughput. Kafka retains messages based on your configuration, not on consumption. You can set time-based retention, log.retention.hours, or size-based retention, log retention bytes, per partition. This enables message replay, allowing subscribers to reread historical events simply by resetting their offset. Proper retention settings are crucial for balancing storage costs and replay capabilities. Log compaction and retention serve different purposes. Time or size-based retention deletes messages based on age or size, keeping the last n days of all messages. Log compaction, on the other hand, keeps only the latest value per key, making it ideal for topics where you care about the current state of each entity. Choose the right strategy based on your use case, event logs versus changelogs. Kafka achieves fault tolerance through replication, leader election, in-sync replica tracking, and durable storage. Producer retries and idempotence prevent message loss on transient failures, while consumer offset management allows consumers to resume from the last committed offset after a restart. With proper configuration, a single broker failure is transparent to producers and consumers. Partitioning is Kafka's horizontal scaling mechanism. Multiple producers can write to different partitions simultaneously, and each partition can be consumed by a separate consumer thread. Partitions are distributed across brokers, eliminating single bottlenecks. Effective throughput is determined by the number of partitions and their individual throughput, so design your partition strategy carefully for optimal scalability. Exactly once semantics guarantees that each message is processed exactly one time, no duplicates, no losses. Kafka achieves this through idempotent producers, transactional APIs for atomic multi-partition writes, and committing consumer offsets atomically with output. ES adds some latency overhead, so use it only when truly required, such as in financial systems or billing applications. Kafka supports 3 delivery semantics. At most once commit offset before processing, risk of message loss. At least once commit after processing, risk of duplicates. And exactly once transactional, no loss or duplicates. Most systems use at least once with idempotent consumers for simplicity and performance, reserving exactly once for critical use cases. Kafka Streams is a client-side Java library for building stream processing applications. It runs inside your application, requiring no separate cluster. Kafka Streams supports stateful operations, windowing, joins, aggregations, and fault-tolerant state stores backed by Kafka topics. It's ideal for lightweight, per-service processing without the overhead of managing a separate analytics cluster. Kafka Streams processes records one by one in true streaming fashion, while Spark Streaming uses microbatches. Kafka Streams is embedded in your app, offering low latency and simple state management. Spark Streaming requires a separate cluster and is better suited for heavy analytics or machine learning pipelines. Choose Kafka Streams for lightweight, per-service processing and Spark Streaming for large-scale analytics. Kafka Template is Spring Kafka's high-level producer abstraction. It wraps the native Kafka producer and integrates with Spring's transaction support. With Kafka Template, you can easily publish messages to topics, handle results asynchronously, and leverage Spring's dependency injection for cleaner code. This makes integrating Kafka into Spring Boot applications straightforward and robust. A Kafka listener is the consumer-side annotation in Spring Boot that registers a method as a Kafka message handler. It supports batch listening, manual offset acknowledgement, and error handling through container factory configuration. This annotation simplifies consumer logic and integrates seamlessly with Spring's dependency injection and configuration management. In Spring Boot, you can handle Kafka consumer exceptions by configuring a concurrent Kafka listener container factory with a dead letter publishing recoverer and a retry policy. Distinguish between retriable errors, like network issues, and non-retriable errors, like deserialization failures. Non-retriable errors should be sent straight to the DLQ and always include exception metadata for observability. In production, you may encounter high consumer lag, frequent rebalances, not enough replicas exception, out-of-memory errors, message deserialization errors, or uneven partition load. Address these by tuning timeouts, optimizing processing, fixing unhealthy brokers, using a schema registry, and distributing keys evenly. Proactive monitoring and quick troubleshooting are essential for stable Kafka operations. Effective Kafka monitoring includes tracking consumer lag, records consumed rate, commit rate, producer error rates, request latency, and broker metrics like under-replicated partitions and ISR shrink-expand rates. Use tools like Prometheus, Grafana, or managed solutions like Confluent Control Center. Set up non-negotiable alerts for critical metrics to ensure you catch issues before they impact your users. Increasing the partition count for a topic is a one-way operation. New messages are distributed across more partitions, but message ordering by key may break, as the same key could now go to a different partition. Existing consumers will rebalance to cover new partitions, but historical messages remain in their original partitions. Plan your partition strategy carefully to avoid future migration headaches. Kafka guarantees ordering only within a single partition, not across partitions. If your business logic requires strict global ordering, you must use a single partition, which limits throughput. Alternatively, implement an application-level ordering layer or reconsider your design, as true global ordering needs are rare. Most use cases are satisfied with parentity ordering. Design your partition strategy by considering target throughput, expected consumer count, and broker count. Use high cardinality keys that distribute evenly, avoid too many partitions per broker, and over-partition slightly for future scaling. A replication factor of at least 3 is recommended for production. Proper partitioning ensures scalability, reliability, and efficient resource usage. Kafka's internal workflow involves the producer serializing messages, determining the partition, batching messages, and sending them to the leader broker. The broker writes to disk, followers replicate, and acknowledgments are returned based on the AX setting. Consumers poll brokers, process records, and commit offsets. Each partition is a series of segment files, enabling high throughput, sequential I/O. Each Kafka partition is stored as a series of segment files, typically 1 GB each. Messages are appended sequentially for O1 write performance, and Kafka uses zero-copy transfer for efficient reads. Index files map offsets to file positions, enabling fast random access. This design allows Kafka to handle millions of messages per second on commodity hardware. To excel in Kafka interviews, focus on must-know concepts like ISR, leader election, and segment files. Understand reliability settings, failure handling patterns, Spring Boot integration, production monitoring, and partition design. Build your vocabulary, practice with real scenarios, and be ready to discuss how you've solved production issues. This well-rounded knowledge will set you apart as a Kafka engineer. The best Kafka engineers aren't those who memorize definitions, but those who can troubleshoot real issues, like identifying a hot partition causing lag and fixing it with a better key strategy. Run Kafka locally, experiment, and read the documentation. Building hands-on experience and a deep understanding of Kafka's internals will help you stand out in any interview. Good luck.